So we're starting chapter 7, which is our last chapter of the quarter. This chapter is pretty straightforward. So we are starting to talking about what if we have multiple phases and how to read phase diagram, how to get information from phase diagram. And yeah, before we do that, we have to talk about phase rule and then the one component phase diagram, and that's about it. I don't think I want to open like new chapters since we only have 3 lectures to go, but we'll see how fast we go on chapter 7. All right, so getting started. So today we'll focus on the phase rule. So this is a topic that's a little bit linked all the way back to our lecture 1. So we'll use a lot of refresh your memory on lots of like definitions and terms that we went over in chapter 1, which is when we first get started in thermodynamics. So a quick review on some of the terms we will be using that include what is a phase and what does homogeneous mean, what does heterogeneous mean. So a phase is typically describing a homogeneous portion of a system. Now, a system of interest could contain several phases, several solid phases, like different kind of solid are considered different phases. Maybe multiple liquid phase. If you think about water and oil, if they're not miscible with each other, you can have multiple liquid phase as well. But usually there's only one gas phase. It's not straightforward to say, hey, I have 2 gas phases that are not mixable with each other. And we did this example in our lecture 1, so just to quickly remind you in how to quickly identify how many phases are there in each system, right? So if we have a cup of still water, then we have only one liquid phase. Iced water, we have 2 different phases. And then iced soda water, that's 3 phases, right? And we can make this a little bit more complicated by say like in here, the ice cube is not only made with water, but we also have ice cubes made of ethanol, which is not technically speaking true, but in that case, you would have 3 phases, right? So the ice cube made of water or the solid cube made of ethanol will be considered 2 different phases. So far, so good? All right. And then we'll dive into our chapter 7.1, which is the phase rule. So in this part, our goal here is to derive a representation of the number of degree of freedom or variance. We use like small letter f to represent the degree of freedom of an equilibrium system. So like what we always do, we start from the definition. We went over like derivation in how to calculate the degree of freedom. Then we discuss the physical meaning of the degree of freedom and then see examples in how do we use it. All right. So getting started, looking at what it means. So in here, we're saying that the number of degree of freedom of an equilibrium system, so this is by definition, we're always talking about equilibrium system. If the system is not at equilibrium, we don't use the term of the degree of freedom. So if there's a chemical reaction taking place, we only talk about the degree of freedom, even if there's a reaction going on, that reaction must already reach reaction equilibrium. All right. And the degree of freedom is defined as a number of intensive variables needed to specify its intensive state. So when we're saying intensive state, we're saying that is a thermodynamic state that's not affected by the sizes of the system. So it's a little bit like the intensive properties, right? So in here, this degree of freedom is specifying how many intensive variables like pressure, temperature, mole fraction, chemical potential. And these are intensive variables that we need to specify an intensive state. So a quick true and false question here would be, well, does the intensive variable include maybe enthalpy? Will enthalpy be part of our intensive variable? Then it's not, right? Because intensive variable is only talking about intensive properties, including like temperature, pressure, mole fraction, your chemical potential, or maybe concentration, etc. And again, like if we have lots of cups of water, right? So the size of your solid or liquid phases in different cups may vary. But in this case, when we're looking at 1 cup, 2 cups, 3 cups, so in each cup, let's say we have the same set of the intensive variables. Then if we have like 10 cups, 20 cups, these intensive variables will remain the same. So that's why we say like these will all have the same intensive state. And again, the degree of freedom, which is the term we're introducing today, is describing how many intensive properties we need to describe an intensive state. All right. So let's get started. But before we do that, I'm going to make 2 hypotheses or 2 assumptions that we might later on drop. So I'm going to write these 2 assumptions on the board so that we can start from a simplistic system that's at equilibrium, no chemical reactions occur, and every chemical species is present in every phase. So let's start from a simple system. So assumption 1, no chemical reaction. And assumption 2, every species is present in every phase. So those are the 2 assumptions, right? And in here, we will be using C to state that's the symbol we will use for the number of chemical species, like H2O, ethanol, NaCl, etc. And we'll use P to describe phases, so gas phase, liquid phase, solid 1, solid 2, solid 3, liquid 2, etc. All right. Now we're just counting how many intensive properties are there. So with both of them true, well, we're looking at a system. Let's say this system, we have 2 chemical species, oxygen, nitrogen, and 2 different phases, gas and liquid. So how many intensive properties are there? In total, without considering the interconnection of these intensive properties, in total, we can simply write, for each phase, we got 2 mole fractions, right? So we have the mole fraction of O2 in gas phase, and we have mole fraction of N2 in gas phase. And likewise, you have O2 in liquid and N2 in liquid. All right, so if we're only looking at mole fractions, it's very straightforward to write. We have like 2 times 2, so 2 species in 2 phases, adds up to be 4. Or we can generalize that conclusion to say the total number of mole fractions existing is phase times component, so P times C. All right. Now, from here, ignoring all the connections between your mole fractions, we can first start to hypothesize. Let's say my variance, F, or the degree of freedom, equals to your mole fraction, PC, plus 2. So this 2 comes from temperature and pressure, right? So these are the 2 intensive properties that's always going to present there, as long as we specify the system is at mechanical and thermal equilibrium. So my pressure and temperature is always defined. Now, obviously, there is a small problem that we need to take consideration within my mole fraction product, because we know my mole fractions are not independent from each other. So we have to take that into consideration. I'm just going to write this is what we start from. So F equals to PC plus 2. Not considering the link between fractions. Welcome in. All right. And considering that, let's think about two different relations that can decrease the degree of freedom from my PC plus 2. So there are two relations that we need to consider. Anyone want to take a guess? What are we missing here? Right. So first of all, I'll get started. We're talking about two different phases that are all in equilibrium with each other, right? So when my oxygen in gas phase and my oxygen in liquid phase are in equilibrium with each other, we went over before when we were discussing phase equilibrium that their chemical potential must be equal to each other when they're in phase equilibrium. That's the first. The other one is sort of more straightforward, right? So the total mole fraction of your oxygen and nitrogen in the same phase will always add up to be 1. All right? So two things that we observe the system and use our chemical knowledge to say there must be, we can eliminate degrees of freedom based on our understanding of phase equilibrium and also what's the definition of mole fraction. So let's see what exactly are those expressions that we want to add in to that degree of freedom equation. First thing, the sum of all mole fraction in each phase will add up to be 1. Or let's say if we have the mole fraction in phase alpha of your species 1, 2, 3, 4, etc., all the way to C, all these mole fraction add to 1. That means we can eliminate P degree of freedom because each mole fraction adds up to be 1. All right, so we're eliminating P because all mole fraction adds up to be 1. All right. What about material equilibrium? We were talking about material equilibrium, or in this case, because we're assuming no chemical reaction is taking place, we only consider phase equilibrium. Now, in our previous discussion, went over phase equilibrium. That is, when my same component, species 1, is in different phases, alpha, beta, gamma, etc. When they are in phase equilibrium with each other, then their chemical potential must equal to each other. All right. So what does it mean? So again, this translates to say in total, we have P phases, and we have like P minus 1 of these chemical potential that have the same value. All right, so we still need a number to represent the chemical potential to start from. But we can only eliminate P minus 1 degree of freedom for every component or chemical species. All right, so for every component, we have this relationship, and hence for every C, for every chemical species, we eliminate P minus 1 degree of freedom. So that's coming from phase equilibrium. All right. So taking together, what do we have? We have this one minus C times P minus 1. This comes from phase equilibrium. Any questions before we move on? No? Okay, sounds good. And then let's solve this equation, right? So in this case, we start from very simplistic way of thinking, like what are the total amount of intensive properties exist in the system, and then remove the degree of freedom based on their connection to each other. And we end up getting, this is PC plus 2 minus P minus PC plus C. Right, so my PC and PC will cancel out. We end up getting my F equals to C minus P plus 2. Well, we're considering, no reactions, and every chemical species exists in every phases under that assumption. All right. And, well, as I promised, we went over the derivation. And then let's look at what exactly is the physical meaning of variance F. So when we're talking about variance F, or the degree of freedom, remember this tells us the number of intensive properties we need to describe the intensive state. Or the other way to put it is, once this F degrees of freedom is achieved, or once the F degrees of freedom is being fixed, the value of all intensive properties of each phases will be fixed. So this sort of goes back to when we were talking about the ideal gas law. Remember, we say, like, for a pure ideal gas, you only need 2 experiments to measure its equation of state and to get everything we want to know about its macroscopic property. So it's sort of related to what we discussed in that case. Yeah.
So we're not necessarily concerned with the degrees of freedom of, like, an individual molecule, how to, like, stretch or scissor, as much as just have a collection of the system.
Okay, so that's a good question, because scientists use the same term in different content, right? So when we are talking about degrees of freedom, we're in thermodynamics. So in thermodynamics, we only discuss a collection of molecules, or the macroscopic properties of the molecules. Now later on, when you learn, like, quantum mechanics and spectroscopy, you'll learn a different terminology of the degree of freedom. But for now, I guess the better way to call it, this is a degree of freedom or variance. All right, and again, let's think about the ideal gas law, right? So in the ideal gas law, when we're having an ideal gas, like a pure ideal gas, what is my C? My C is 1, my P is also 1, and I have 2 degrees of freedom that I need to describe all the intensive state of my ideal gas. So in my ideal gas, what do we have? We have PV equals to nRT, or PVM equals to RT. So as long as we know, like, say, P and T, or P and VM, or VM and T, we'll be able to tell, like, what is the other term. And also we'll be able to tell other properties, like, for example, what is the density of my ideal gas? What is my CPM? What is my molar heat capacity of my ideal gas, right? So these terms will be defined if we define, like, 2 different intensive properties. So that's what the degrees of freedom or the variance mean, or why do we care about it? All right. Now we still have 2 assumptions, and obviously we hope we can generalize our phase rule as much as possible by dropping these assumptions. So let's think about the first one. Now let's imagine we're dropping the second assumption. I don't know why I dropped the second on my lecture note, but let's do that. Let's drop my second assumption, which is saying, what if you do not necessarily need all chemical species in every phase? So now you can have, like, a cup of salt water and a saturated salt water, like NaCl, right? So the NaCl can crush out to be a solid, but in the solid phase, you do not have water present. So let's think about how can we generalize that. So what does it mean? Now we say species I might be absent from phase delta. These are just random, numbers of species and phase. So this tells me my number of intensive variable is reduced by 1, and then the number of relations is also reduced by 1. Let's use an example to see what does these two statements mean. So again, the example we're picking here is a pretty straightforward one. We have a saturated aqueous salt solution with pure solid salt. So in this case, in my solid phase, what do we have? I have a cup of saturated salt solution. So in my solid phase, we only have my salt, which is, let's say, NaCl. And in my solution phase, I have my NaCl and H2O. I know the NaCl dissociate, but let's assume it doesn't dissociate because we are still holding my first assumption. We'll go into that later. So in my solid phase, what do we have? Using the same kind of logic, starting from the very beginning, now instead of PC, right? So what we have the chi H2O in the solid phase equals to 0, or the mole fraction in my solid phase is no longer a variable. So we have one less variable. So this is what we mean by we say we have like one less variable. All right. And what does it mean when we say the number of relation between the variable also minus 1? Well, H2O is no longer present in solid phase. So when we're thinking about phase equilibrium of my water between solid water and liquid water, this equilibrium no longer exists. So this is what we mean by relationship between variables also reduced by 1. All right. So, I mean, the actual derivation of proof is slightly more complicated, but I just want to use this example to demonstrate, like, having this assumption 2 dropped doesn't necessarily change our conclusion here, that the variance equals to C minus P plus 2 will still hold true, even if when some of the species does not appear in every phase. We're still assuming no chemical reactions at this moment. All right, and let's see one of the examples that we have. Let's say, find the, yes?
Going back to that last thing, would that be because C and P are both decreasing?
Correct. Yeah. Okay. The other one. Okay, so C and P are not changing, right? So in this case, we're talking about the actual relationship. So it's like when we're counting it in there, right, we start from like PC. So what we're saying is we cannot use PC when something is missing in your phase. Like previously, when we were talking about the original case where 2 components and 2 phases, in total we have 4 more fractions. Right? But here, because H2O is missing in the solid phase, so we only have 3 more fractions. So it's slightly different. It's a little bit oversimplification to say both C and P are changing. I try not to mix that term. Okay, so let's see how do we use this. So the question asks, find the variance or F of a system consisting of liquid solution of methanol and ethanol in equilibrium with a vapor pressure of methanol and ethanol, and give a reasonable choice for the independent intensive variables. All right, so what do we have? Well, how many components do we have in this case? So C equals to 2 methanol and ethanol. P equals to 2, that's liquid and vapor, right? So my F, well, equals to 2. Right. And the question asks us to find independent intensive variables. So you can pick whatever you like. as long as they're not internally connected to each other. We went over 2 cases that are internally connected. Like it is not true, I'm just gonna give you wrong examples, that if you provide the more fraction of methanol vapor and more fraction of ethanol vapor, like that's not good because they're internally connected to each other. Or if you give the chemical potential of methanol vapor and the chemical potential of methanol liquid, that's also not good, right? Because they're internally connected to each other. So this can be like a true and false problem. I'll give you, like in this case, you only need you only need 2 intensive Okay, so in this case, we'll give you the setup. We say like we provide you with 2 intensive properties like these 2. Are they defining? Are they enough to define the intensive state? And the answer is not true if they're not independent to each other. Okay, so that's a quick practice. And let's now look back to our assumption 1. So this will try to replace my assumption 1 here. And I'm just going to rewrite that F equals to C minus P without chemical reaction. So that's the general phase rule when there's no chemical reaction taking place. And let's update this one, considering now chemical reactions are taking place. So in here, how we're introducing more connection when there's a chemical reaction taking place. So that depends on several things. First is, well, how many of the chemical reactions are taking place. And when we say chemical reactions, again, these must be independent chemical reactions. So remember back in the Hess law when we were talking about, build the third reaction coming from other known reactions, right? So if you can build a reaction from the other reaction, then they are not independent reactions. We're only counting the number of independent reactions. And for every independent reactions that are in equilibrium with each other, and since we are here, let's just quickly review what we know, right? So this is a general form of a chemical reaction, stoichiometric coefficient, reactant or product. And when we're having an equilibrium condition, we effectively have the sum of your stoichiometric coefficient times the chemical potential of each species adds up to be 1. So in this case, because of this relationship, we say that this gives us a way to link my intensive properties of each component, the chemical potential of my each component in a chemical reaction based on the reaction equilibrium. So for each independent reaction, now we have it called R, we will eliminate one variable. And the reason we're eliminating one variable is because of the relationship of the chemical potential in these reactions. All right, so with reactions, this then becomes F equals to C minus P plus 2 minus R, and R is my independent chemical reaction. Okay. The next one will be a little bit chaotic. Then we have the system-specific restrictions. I have to mention it because they do exist, but these are less general and more questions tend to arise for these descriptions. For example, if we have equilibrium in a closed system containing only NH3. And in this case, when we're looking at the system, we can say that even if we only have like this one reaction taking place, all of my N2 gas and H2 gas will come from the decomposition of NH3. Or if we're looking at the relationship between the mole fraction, right? So this relationship will be fixed based on its stoichiometric coefficient. or in this case, your mole fraction of H2 will always equal to 3 times the mole fraction of N2. And this is called an additional relation, or abbreviated with A. I wish to give you a more general description, but unfortunately, these are called system-specific restriction for a reason. It's more like system by system. And that's minus A, so additional. Yeah.
In this case, what would A equal?
1. Right, because we have this 1 relationship between your H2 and N2. And also NH3. It's just the relationship of the mole fractions of the 3 component we have. So, as a general phase rule, right now we dropped all of our assumptions. We're ready to summarize our general phase rule. What we have my variance F equals to C minus P plus 2 minus R minus A. What are these terms? C is my component, right? So number of species. P is phases. You practice counting the number of phases earlier in chapter 1, so now it's another chance to practice, right? Whenever you have like a cup of saturated water of like NaCl and magnesium Cl, you have participation of, like, you have like solid crystal that crush out of NaCl and like magnesium chloride. How many phases are there? So those are practice problems in chapter 1, so it's time to review them. And we have 2, so this 2 comes from temperature and pressure. They must exist. We must well define temperature and pressure to ensure we're at thermal and mechanical equilibrium. And we have R. Here is independent chemical reactions. Right, so an independent reaction just it cannot be an addition of different reactions. Like what if we have like A plus B goes to C, and then we have, let's say, A plus D goes to E, and then we have a new reaction called like 2A plus B plus D goes to C plus E. Now this is not a real reaction, it's a sum of the other 2 reactions. Dun, 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 dun. Okay. And let's see. And then we have our additional factor. So this is specific. All right. And to make our life simpler, typically chemists will define a term called independent component. So C, IND, that's independent component. And that equals to C minus R minus A. So that's taking consideration of reaction and any potential additional relation that we have. So in that case, we can finally rewrite it to be my F equals to C IND minus P plus 2, where your independent component include chemical reactions that might have taken place. And in here we have a few, keywords to make it more strictly correct. That's no word of separating phases, PV work only, closed system. And again, we only discuss degree of freedom for equilibrium systems. We don't use the term of degree of freedom or variance to describe reactions that has not reached equilibrium. And let's look at an example together, shall we? minus R minus A, F equals to C, T minus P plus 2. All right, let's look at an example together. This part should be pretty straightforward. It's just like lots of things. We're imagining scenarios that's taking place to help you to understand a pretty straightforward concept. And then we're talking about application of the phase rule to calculate the variance of a specific system. So read it. We have F, find F in a system consisting of the carbon calcium carbonate solid, calcium oxide solid, and carbon dioxide. And we're giving you this additional information that all calcium oxide and carbon dioxide come from the reaction of calcium carbonate decomposition into calcium oxide plus CO2. All right, so let's see what do we have. First thing first, let's just write out what are my C, R, and A to calculate for my independent component, CINT. So my C here, we have 3 different things. We have one reaction taking place. And then that additional one is a tricky one. You would tend to put 1, but in this case, the tricky thing comes is that the CO oxide solid and my CO2 gas and also my the calcium carbonate are in different phases. So my CO2 is in different phases. And when we're talking about this additional factor, we're talking about the mole fraction of calcium oxide, equals to the mole fraction of CO2 if they are in the same phase. But because my calcium oxide and CO2 are not in the same phase, this relation is not a valid relationship. And that's why this A is actually 0. All right, so do give it a more careful thought, even if the question is stating something very similar we saw in the classroom. So doing that calculation, we get my independent component equals to 2. Next question, we have the C independent. We need to find out phases. The next one is talking about phases, right? So here's a quick reminder of the phase is a homogeneous portion of a system. A system can contain multiple solid phases, several liquid phases, and only one gas phase. So in our example here, we are looking at 2 solid phase and 1 gas phase. So in total, we have my P equals to 3. All right, 2 solid, 1 gas. And then just plug in the numbers. I think I don't need a calculator for this. We have 2 minus 3 plus 2 to be 1. Or the other way to put it, in this system, as far as you limit like temperature or pressure or the mole fraction, you will be able to get the same kind of intensive property or intensive description of the system. All right. I only have 10 minutes left, but I do want to quickly introduce the phase diagram, the one component phase diagram, and I'll leave a question for you to think about. So let's get started. So this is 7.2. Using the phase law, when we're looking at the one component phase diagram, what can we get? Thinking about a scenario of a pure substance. And depending on, and think about if we have a specified temperature and pressure, how many phases can coexist with each other. Or in this case, we have if my F equals to 0, that's like if my temperature and pressure are set, right? And then we have my 1 minus P plus 2 equals to 0, so my P equals to 3. So this is going back to connect it to our phase diagram. We always say like for a pure component, it can exist only a maximum of 3 phases in equilibrium with each other. So that's our triple point. So for every species, there will be a triple point of which its liquid, gas, and solid phase are in equilibrium with each other. But whenever these 3 phases are in equilibrium with each other, the temperature and pressure must be set, or the triple point of a given pure species must be set at certain temperature and pressure. And then reading our phase diagram, I mean, we have so many different lines here, right? So one of the things is we see like at here, it's like using this dash line to tell you where my triple point is. And what about along the lines of my phase diagram? For example, if we're looking at the line of AD, that's our, phase equilibrium between my solid and liquid phase, or that's the melting of your solid, or the solid-liquid equilibrium whatsoever, right? So we're talking about equilibrium between 2 phases of one component, and hence we have F equals to 1. All right, so you have 1 degree of freedom along this line. So your temperature and pressure are not set at a specific value. They are related by some kind of relationship. All right, so it's like your temperature and pressure, they're a function of each other. So that's where this line comes from. Same applies to my line OA. So that's your gas-solid equilibrium. Again, it's F equals to 1. There's a relationship between your temperature and pressure along that solid-gas equilibrium. And the same to A to S, right? So that's your liquid and gas equilibrium. So my question here is, can you use the things we learned before to plot the molar Gibbs free energy of H2O from the point going from, let's say, R to S, and then S to Y? We're talking about the equilibrium between your gas to liquid. You can assume all gases are ideal, so you can use PV equals to nRT if you like. And you can assume the volume of the liquid does not change when the pressure change is small. All right, so let's just assume the volume doesn't change along with the pressure along this curve. So this feels like something that's like, how do I even approach this question? So I'll give you a heads up to see like how to approach these kind of questions. First of all, thinking about, we're plotting the molar Gibbs free energy of a pure component. And for the process between my R to S, what phase we're in? We're in one single phase of ideal gases, right? So if we're considering the process between R to S, which is a single phase process, we have my GM, the molar Gibbs free energy of H2O, equals to the chemical potential of your pure H2O in your vapor phase, in both cases, in your vapor phase. And then from there, what else do we know about our Gibbs free energy? We have our Gibbs equations, right? So we have my dgm equals to negative sm dt plus vm dp. That's our Gibbs free energy. In here, these are straight lines. Now, what is my x-axis? My x-axis is my temperature. So my R to S process is a isothermal process. And that means we know that my dt equals to 0. So far, so good? So that means my dm got to be simplified into Vm dp. Right? So for ideal gases, do we know what is my Vm? For ideal gases, my molar volume equals to my RT over P dP. And then you take the integral on both ends, we end up getting Gm equals to, well, integral of RT over P dP equals to RT ln P. All right, and thinking about what are we trying to plot? You're trying to plot how does Gm change. And in this process, the only thing that's changing is pressure. So we're plotting how does my molar Gibbs free energy change with respect to pressure. And the first part of my curve between R to S is a natural log function. Right, so this is the same as, say, we have like some kind of function fx equals to some constant a times natural log of x. Your R and T are constant in this case. The pressure is what we're trying to plot. Right, so that's the first half. Now I'm going to leave it for you to think about, what about at point S? What is my molar Gibbs free energy at point S? And how to plot my molar Gibbs free energy change with respect to pressure after we're in the liquid phase. And we'll pick up from here in our next lecture to go over how I will do it. All right? All right, that's everything from me. I guess happy Thanksgiving. Next week, I'll be here with you next Monday and Tuesday. Keep that in mind. And then Miranda will be with you next Wednesday and Thursday. And I won't be here next Friday. All right?